Great. Thank you so much, Xiaowei. And I'd really like to thank all of the organizers of this event. It's been a really fantastic week. And thanks to all the speakers as well. I've learned quite a bit. So I will be talking on topology in machine learning. First, let me just also say that I'm quite interested in how academics are sharing our activities freely online these days, such as this conference right now. So I'm involved in a group called AATRN. If you want to Google search it, it stands for Applied Algebraic Topology Research Network. But we do a lot of online activities in applied topology. We're running our second interview series that we just had the first interview this morning, and doing video tutorial-a-thons for early career members to share their work. So I'm quite interested in chatting with folks about topics related to online networking in academia. So what I want to describe today is applied topology and how it relates to machine learning. Applied topology is my area of training, and the area has recently grown a lot due to interactions with machine learning. So we're quite excited about continuing in that direction. So I'm a mathematician, and geometry in my mind is the closest mathematical topic to physics, right? If you think of how a physical system evolves, it's often a geodesic, a shortest path in a geometrical space-time. But geometry is quite complicated. For example, if I take this image of a flock of birds, there's so much geometrical information here. If I have 1 million birds, I have 1 million choose 2 different distances between pairs of birds. And you can see lots of local structures, you can see lots of global structures, and it's really difficult to make this geometry amenable to machine learning models. It's also difficult when the machine learning model gives a prediction, such as we predict this flock of birds is going to move in this way next. It's hard to say how the geometry informed that prediction. So by vectorizing geometry, I mean taking geometry and turning it into a suitable input for machine learning. And I also mean using geometry as an explanation for why a machine learning model made this prediction. Okay. Next, I will move on to an introduction to persistent homology, which is one of the main techniques in applied topology, and explain how persistent homology can be used to vectorize geometry. And then after that, I'll describe some applications, mainly in material science, and how we can use this for explainable machine learning. So let's move on to introduce persistent homology. Persistent homology is sort of a topic that merges geometry and topology. What's the difference between geometry and topology? They're both areas of mathematics. A geometer would care about the distance between points on this coffee mug, or the curvature on the inside or the outside of the handle of this coffee mug. Whereas to a topologist, things like distances, and curvatures are not important. To a topologist, this coffee cup on the left is the same as this solid donut on the right. And you can see a deformation, how I shrink away this mug without ripping or tearing or gluing anything to deform from the coffee cup to the donut. So the classic joke is that a topologist is a mathematician who can't tell the difference between the items he's using to enjoy his breakfast. What topology does preserve is holes. So we have one hole in the coffee cup, just like we have one hole in the donut. So you should almost think of geometry as a continuous infinite invariant. There's an infinite number of distances or curvatures on the space, whereas topology is more of a discrete computable invariant. There's just one hole. Okay. So topology is computable. We can compute something called homology, which counts the number of holes in each dimension using linear algebra. So just like a lot of machine learning is based on linear algebra, so is homology, which counts the number of holes in a space. So we have 0-dimensional holes, 1-dimensional holes, and two-dimensional holes. The dimension, I'm just indicating by the subscript. Zero-dimensional holes are just connected components. So 6 connected components, which is why the zero-dimensional homology is rank 6. One-dimensional holes are one-dimensional loops. So this space here has 3 one-dimensional holes. If I have a hollow sphere that has a two-dimensional hole, it has a two-dimensional hole because you could fill the sphere with jelly and the jelly won't spill out. So I have a two-dimensional hole. A torus has a single connected component, 2 one-dimensional holes wrapping around this way or this way. And the torus has a single two-dimensional hole. It's a hollow torus. If you fill it with jelly, the jelly won't spill out. Okay, that's homology. Persistent homology is tracking homology as you have an increasing sequence of spaces. So start with the data set and then make it larger by adding in edges, triangles, tetrahedra, etc. Via this increasing scale. So now what we're going to do is we're going to track the homology at each point in time. All right, so at this point, we just have many different connected components. Each connected component is encoded by an interval in this zero-dimensional barcode. Once we get to this stage, everything's all connected up. We just have one connected component, and that's tracked by this single zero-dimensional interval. At this stage, we have loops formed. We have 2 loops measured by these 2 intervals. One is quite small, maybe just an artifact of sampling noise, whereas another loop is much larger. At this next stage, you see that one of the loops fills in, and that's why this interval dies. And then finally, at this last stage, we have no more one-dimensional holes. So persistent homology is computable. It's computable because it's tracking topology at each point in time. But it also measures geometry. It measures geometry through this growing sequence of spaces. And this growing sequence of spaces is what allowed us to identify the small hole corresponding to a small bar and distinguish it from this larger hole corresponding to this larger bar. So persistent homology is one answer to how to vectorize geometry. You can compute persistent homology whenever you have an increasing sequence of spaces. Another common way to obtain an increasing sequence of spaces is when you have a function on a space. So I've drawn this surface on the left, which is a real valued function on the squared. And these images are made by my graduate student, Lander. What we'll do is we'll produce an increase in sequence of spaces in the middle by raising this function value, this sheet on the left, and including all of the sublevel sets. So all of the regions of the domain that are beneath that function value. So we start with this crescent moon, whereas as we raise the level, we complete to a circle, and then an extra connected component forms. And then eventually that connected component merges and the entire hole fills in. So to be quick, the red bars are the connected components. So we have one connected component. The blue bars encode one-dimensional holes. So this blue bar is encoding this one-dimensional hole. We get a new connected component here. It merges to what we had before. So that interval ends. And eventually when the hole fills in, that's when this one-dimensional bar ends as well. All right, so for example, you can apply this to image data, such as images of clouds. You include the pixels that are below a certain intensity, and as you raise the intensity, you can track the texture of the cloud. So these barcodes are sort of a geometric summary of texture of different clouds. A dual representation instead of the barcode is as a persistence diagram. So let me briefly say how you go from the barcode to the diagram. I'll draw the diagram where I include the one-dimensional persistent homology information. So the one-dimensional holes. All right. So in this barcode, I have two intervals, and that's why I'm going to have 2 points in the diagram. And I just look at the birth value and the death value of each interval. And then I plot a point with birth coordinate and the death coordinate. And the death is always after the birth. And that's why these dots in the persistence diagram are always above this diagonal. You know, if I have this birth and this death, then I get this point down here. Okay, so the distance above the diagonal just tells you how long the interval was. So if you take your intervals and sort of lie them on their side, then you get the points in the persistence diagram. So the points in the persistence diagram that are far away above this diagonal are features that lasted for a long range of scales, whereas the points in the diagram that are near to the diagonal are more local features, holes that appeared and disappeared soon after. All right, so for example, we can summarize the geometry in brain artery trees. Here we have a young 24-year-old brain and an older than 24-year-old, I suppose, 60-year-old brain. A lot of the knottedness or local geometry of your arteries decays a little bit as you age. And that appears in the persistent homology diagrams as follows. We have more points in the persistence diagram for the 24-year-old brain than we do in the 60-year-old brain, measuring some of this local geometry that's present in the younger brain, but not the older one. And this has been used successfully in machine learning tasks to identify ages, for example, of brains. I now want to move to applications in material science and point out how this vectorization that represents geometry can be useful in explaining why machine learning models is making one prediction versus another. So I'll start in material science. So folks have used this on a lot of different data, glasses, near periodic formations, metals obtained by ion bombardment. So whereas this has been used on real materials, I'll describe things on a synthetic example. We have two classes of materials. The ones on the left highlighted in blue and the ones on the right highlighted in red. And what we can do is we can produce persistence diagrams that vectorize the geometry of these various materials. Now, after you train your machine learning model, maybe a very simple one like a linear regression, logistic regression, or support vector machine, you can ask what areas of the persistence diagram were the most discriminative for this task, distinguishing material A on the left in blue from material B on the right in red. And what you find is that points in the persistence diagram here, maybe earlier birth values, not persisting quite as long, are characteristic of this blue material, whereas points in the persistence diagram, one-dimensional holes that live in this red region, are more characteristic of this material on the right. And now you can take a particular material sample and zoom in and say, what were the holes, as I increased the scale and sort of expanded the space, what were the holes that biased me towards guessing this was of the red material type versus what were the features or the holes that biased me towards guessing that this was the material of the blue type. So you get an explanation on the material. What is the geometry that led me to predict this was either coming from the red class or the blue class? This particular sample is from the blue material class. It has more blue local geometry holes than it does red. So I enjoyed this plot in Yi Zhang's talk from yesterday, where he described this trade-off that's not always there, but is sometimes there in machine learning algorithms. And I apologize that my text has gotten corrupted, but sometimes there's this trade-off between accuracy and interpretability. My work has mainly been on these easier to interpret machine learning models. Okay, But folks in my area have also studied how to input persistent homology into neural networks and deep learning as well. All right, so let me end with one last application to statistical physics. So this is from the Ising model. It's a way to study phase transitions. You have low temperature configurations of spin or high temperature configurations of spin. And from these samples, you can produce persistence diagrams that encode or vectorize the geometry of that sample. They're drawing a representation here where they sort of translate the diagram to take this diagonal and lay it flat. Okay. But in any case, you can ask, what were the regions of the persistence diagram that were characteristic of the low temperature samples versus the high temperature samples? And you see that right here. So the high temperature samples had persistence diagram points in this region that were a little bit more persistent. They lasted a little bit longer. They were bigger holes. Whereas the low temperature in blue was more characteristic of this region. You had holes that were born earlier and didn't last as long, these smaller holes that we see here. So we get a little bit of interpretation as a result. When we apply machine learning classification on these persistence diagrams, we can go back and ask what were the geometrical features that were characteristic of making a prediction that, you know, this is a low temperature simulation versus a higher temperature one. All right, so allow me to end there. In summary, I've described the importance of inserting geometry into machine learning, much an analogy with inserting physics into machine learning. Persistent homology is just one way, but a popular way to try to vectorize geometry. And it allows you to input geometry as a vector in order to make machine learning predictions. But it also allows you to do the inverse problem of going back and saying, what were the features, the geometrical features of my data set that led me to make one prediction versus another. So thanks so much for your time and attention.
Thanks, Henry. It's very interesting talk. And we got a few questions on Slido. The first question is, so you have given a few examples on using your method to handle or to find the spatial aspect of data. But is there a way that your method can be extended to handle the time dimension or both time and space?
Certainly. So I didn't describe models of collective motion or self-organization, but think of a flock of birds or school of fish or moving aphids. And there's a whole industry now. How do you vectorize persistence diagrams over time? So think of a time varying sequence of persistence diagrams. And I've worked on this time problem as well. And folks have done good work here. So they've been able to say that the way aphids move on leaves, they've been able to reject the null hypothesis that aphids ignore their neighbors. And instead, it's a collective motion model that you need where aphids move according to how their nearby neighbors are situated relative to them.
Yeah, thank you. And another question is, could persistent homology be also used for dimension reduction before training a deep learning model? And if so, if there are any reference or previous work being done on this topic?
Sure. In some sense, you can think of persistent homology as a summary. It's a summary of the geometry. So it's inherently reducing dimension. You know, you can't encode all of the million choose two pairwise distances, but the persistence diagram, this barcode, is a much dimensionality reduced version. So, and there are papers specifically on how to input persistent homology into neural networks. So I'll find you on Slido and see if I can add some references there.
Okay, thank you. And the last question is if you could also give some examples about like real applications or problems which can most likely to benefit from your method.
Sure. So I would say instances where you think local geometry plays a role. So let's look at these materials here, right? There's some sort of texture or shape that's describing the characteristics of this material. So if you think local geometry, texture, shape is playing a role in maybe how a human would identify one material from another, then this is a way to try to add some of that interpretability into machine learning, potentially as well.
Okay, yeah, that makes sense. Thank you so much. Yeah, that's all the questions. Thank you.
Thanks so much.